All right. So welcome to the folks in the room here, and to those of you joining online. If this is your first time joining, my name is Scott Williams. I'm the Research and Education Coordinator at the Wisconsin Energy Institute, and I'm the coordinator and instructor of this Sustainable Energy Seminar Series, which is something we do every other week in the fall and the spring here at the Wisconsin Energy Institute. And our goal is to highlight the cutting edge research and education around clean energy and energy sustainability that's taking place in Wisconsin and in UW-Madison. And our goal is to showcase how different disciplines understand energy challenges and develop innovative solutions. So throughout the series, you'll hear from experts in science and engineering, as well as social sciences and humanities, and with the goal of really learning about the myriad ways that people are doing really cutting edge work in this area. This seminar is open to the public, but is also a class for students in the undergraduate certificate in engineering for energy sustainability, as well as the master's in sustainable systems engineering. The webinars, as you all can see, are open to the public as well. And you're all welcome to join us here in room 1115 of the Wisconsin Energy Institute. I do have live captioning turned on. If for those that need it, you can click on the show captions button in Zoom. And if you have a question online, please use the Q&A box. I'll be monitoring that. We'll probably ping pong between in-person and online questions for the Q&A portion. So with all those logistics out of the way, I'm pleased to introduce our speaker for today. Professor Rebecca Larson is an associate professor at the Nelson Institute for Environmental Studies. Her research interests include all areas of biological waste, which include manure management, handling and treatment of agricultural waste, diffuse source pollution, agricultural sustainability, and waste to energy technologies, including biogas production from anaerobic digestion, which is the topic for today. We are seeing a lot growing interest, especially in recent years, in utilizing waste to energy systems to produce biogas, which can be used in many different systems, which Professor Larson will get into. So I will turn off my microphone so she can turn hers on, so we don't have any audio feedback issues.
I'm glad I didn't ruin anything. All right, so thanks everybody for coming out on this Wednesday afternoon. I guess those of you in course, thanks for all of you who made the trip in the cold weather. I was emailing Scott earlier. I was like, my garage door froze this morning, so I couldn't get my car out, and I was like, uh-oh, it's an old house, so it's just like a freestanding garage, and there is no door except the garage door, so I was like, this is an interesting predicament. But it warmed up so much that my garage door started functioning. So I'm here today, and I'm going to talk to you about digesters. I have given some version of this talk so many times, so please feel free to ask questions. I'm happy to talk about something related or get in more detail on one component. I probably don't give the same talk every time because I just use pictures, and then I just kind of wing it on what I'm wanting to talk about that day. Usually it's the same kind of stuff. I hit the same points, but a little different flair. I've been here about 13 years. I'm an associate professor. I am an engineer by training. I got all my degrees in a biosystems engineering program. And then I just recently moved to the Nelson Institute. I work on a lot of sustainability related things. So I work on digesters and waste and energy and food systems. My focus when I'm like, if I was to say where like my technical expertise would be, it's like on waste processing, waste handling systems. But then as I've worked through my career, that's become a lot into like environmental impacts and doing life cycle assessment and health impacts. And, you know, if you say yes too much, you kind of end up doing all kinds of things that you don't know what you're doing. All right. So I just like to start with this kind of slide because I didn't have to make it, a graphic designer did it for me. But really just talking about sustainability. So a lot of the work that I do with digesters has to do with farm scale digesters, but there's all kinds of digesters out there. You know, you see some for food waste, some for municipal organics, all kinds of different things. I would say wastewater treatment plants are probably the most numerous types of digester systems that we have. They all function kind of pretty much the same technology, just the operations and the handling of them are a little bit different in one context versus the other. In a livestock system, we're trying to make things more sustainable. And so we'll take manure go through some kind of processing. This is where the digestion would be. We try to go through storage sometimes, put it on the crop, back to feed, back to animals, right? So with this system, when you're integrating into this, you're trying to make this sustainable system. I think of digesters as like, I don't just solely work on energy. I think of it as like one of the things I could put in this cycle, right? And I could make this cycle different. I could make this about municipal organic waste, right? Even though a lot of times that ends up in a landfill. You could make that more sustainable into a loop of like a digester or composting and back out into the land, like produce more food, right? So you could kind of make this circle out of a lot of different systems. Again, in livestock systems in particular, which is going to be a little bit of focus, but I guess I don't have to do that for this energy course. I typically talk to people about digesters in Wisconsin, focused on ag systems. So if you want to talk about the other ones, I'm happy to. But in general, again, I think of it as like a processing system. I call it processing because it's not necessarily, when I like as engineering training, we would say treatment is trying to end up with some kind of specific outcome, right? A treatment system, you're trying to attain an output that meets a certain characteristic, right? Is what I consider like a treatment system. So if I'm going from manure to clean water, I'm trying to hit some kind of certain goals for the water to meet those goals through the treatment system. Processing, I'm trying to collect something from this. I'm not necessarily aiming for where the manure is going to end up, but I'm trying to gather something. So it's kind of a processing system that I integrate into the system. Livestock systems, I don't know, do a lot of people have an ag background here? No? One? Yeah. Okay, that's all right. You know, we live, you eat food, you know, you're not too far from it. But in a livestock system, manure is produced, right? And then it's land applied. It's kind of similar to human waste, except human waste goes through the wastewater treatment system, and the digester, they collect sludge, whether they have a digester or, you know, settling tanks, whatever, and that goes out to the land and they treat the other stuff to clean water, right? So there's different systems, whatever you're capturing, a lot of it ends up in the land application part. And so the digester is going to treat some of that. Or process some of that. The reason I like to highlight the difference is because a lot of people will be like, oh, I had a student group that came to me and they will put it in a digester and it'll all be done, right? We're done then. But no, you still have manure or waste or whatever you put in. On the opposite side, you've just lost some constituents in the biogas, right? You still have to handle the product on the other end. It's not like magically transformed. A friend of mine gave me this picture from Pennsylvania where this is a manure storage and it's on fire. I don't show this because it's like, hey, this is dangerous. This doesn't happen really very often. I guess it can. But the point is it's burning methane off the surface of this, right? Because the microbiology in manure, and it's in a lot of different kind of human waste, it's also within there, can degrade the organic matter and produce methane, right? So that's a byproduct of its degradation when it's anaerobic, meaning when it's an environment that has limited oxygen. And so it's just producing this, it's a natural process of what happens. And you can, you know, hopefully we don't light it on fire in a manure storage. Instead, maybe we'll try to capture it and use it in a digester. There's a lot of potential for growth in renewable energy capacity. Just like to show, we don't add a whole lot of bioenergy each year. This is globally, and even in the US, it's even smaller. The percentages of our renewable energy in the US is something I always, from a different presentation, it's like 12% or something. Depending upon your region, that can be greater or less. And the existing capacity of bioenergy isn't that huge. But there's a lot of potential there because it has some flexibilities and building out a renewable structure that has benefits compared to maybe some of the other technologies. So like, what are our limits to wind and solar? Right, our environmental conditions. Yeah, you can, sorry, I caught your arm too late. You can just yell them out too, you don't have to raise your hand. So we have some limits, right? Hydropower has just kind of been around for a while. They always are putting more hydropower in, but solar's been going in really a lot lately. Why is that? Why are we seeing so much solar? Cheaper, right? The prices went down quite a bit. We're seeing a lot of wind, not as much bioenergy, but bioenergy has that potential that solar, right? If you're not in an area where it's super efficient, maybe it's not the best choice to make. Maybe you don't have a lot of sunshine or enough to be productive, or you do and nighttime comes, right? And maybe a lot of your energy use is at nighttime. That was probably the point I wanted to get to. The wind also, you need to be in the right area that is going to generate enough for that to be efficient. Digesters and bioenergy a lot of times have this capacity that storing gas is a lot cheaper than maybe storing the like produced energy in batteries or other things. So you have the potential to fill these gaps and to have gas kind of being produced at a place. Storage is not super expensive for that. So then you could then drive it into generators or other things to produce electricity in times that are critical. I'm going to show you a direction that's not electricity, biogas, and a little bit later in the potential, but just a little bit to look at the mix and the importance of kind of the dynamics as they start to build more resiliency in grids. So we just talked about price tag, right? So I kind of like this chart because it has this like grayed out fossil fuel general cost range in the middle here, right? And you can see when we were talking about large scale solar installations, that huge change in about the last decade in the drop off of prices there is what is making that so competitive. And then we see where is biomass. So biomass is over here. It's always not been super high. I would say there's a lot of operational challenges with biomass energy and some other things that make it a little bit difficult. And you can see the range of it is pretty large as well, but not totally outside of the realm of reasonable compared to some typical fossil fuel replacements. All right, so people get digesters. They're great because they have, so you can produce energy, renewable energy, right? You're kind of using a waste product, capturing something else. That seems kind of great. You're making something. People ask me how I got into these kinds of fields. Besides love working with shit, you're like, all right, well, you make something that people think of as terrible into something you can gain a product from that. That's kind of a beneficial thing. It can reduce greenhouse gases. It gives you some flexibility. It reduces odor and pathogens, and it has all of these other benefits that are really great. So what is it, right? So we showed before that picture. So it's a biological process. It breaks down organic matters. In the areas I work in, they call those feedstocks. I just say that because in different industries, you're kind of looking at different terms for things. I was at a grasslands conference and people got really confused. So the things that go into the digester, I'm going to call feedstocks. You're in anaerobic conditions. So the microorganisms those types of microorganisms can take over, and their byproduct is methane and CO2, right? So there's some other little things in there. Sometimes people also call this dye gas in certain industries. I think in the landfill space, they'll call it dye gas more because there's two primary products. I would say typically you're looking at methane in the range of like 60 to 65%. Then the rest of that is carbon dioxide. There are some little like hydrogen sulfide and some other things that cause tons of havoc and are annoying, but they're at really low concentrations compared to what you see here. So here's kind of a picture of agricultural digesters in the US. I can never really find a great map for ones at like wastewater treatment plants because they track them differently, even though we kind of work in different spheres. And I think that generally happens because at a wastewater treatment plant, they have engineers running digesters and they're trying to hit certain parameters for their overall treatment process efficiency. In an agricultural setting, you typically aren't going to have a lot of engineers running these in the US. They're operating them, trying to get them to produce biogas just for sale. The other parameters, if you have more pathogen kill, that's great, but I haven't really met a lot of producers who are actively driving at trying to reduce that. So a little bit of a different scheme, even though the process is the same. You can see the scale kind of shows how big some of the digesters are. You see a lot of like, there's a lot of big ones in green that are going in on a lot of hog facilities. You definitely see around the country in terms of livestock that certain types of livestock concentrate in an area. That's typically because of the ancillary systems that are around, like, you build up things like, hey, I need to bring my milk somewhere. I need to bring my animal somewhere. So they kind of tend to congregate because of resources in one location. And then you'll see in Wisconsin, we have a lot of smaller systems, mostly all on dairies. That I would say a few decades ago, a lot of them went in, and now all of a sudden we're seeing a recent development. So we'll see more dots and maybe a little bit bigger dots as these maps are updated. I think this one was from 2021. There's quite a few systems, and some are kind of transferring from making electricity into other systems. So that's kind of the picture here.
Just want to like,
yeah.
It seems like these, operation is massively bigger in general.
Yeah, and I would say the systems in general function differently. So I would say like hog systems, they're run differently. A lot of them are run by larger corporations, and so you get producers who have massive amounts of animals in one location. I would say in Wisconsin, we do have some big farms, but they're not anywhere on the scale of maybe what you're seeing out in, you can see the bigger red dairies and the bigger circles out in California. We're seeing a little bit shift, but we have a different kind of setup where the dairies kind of operate. Some are in co-ops and give milk, but then they sell their milk to producers. Whereas like in the hog systems, you'll definitely see more of the things owned by the larger corporations. And so it's a little bit different system. I know I talk fast. Is it boring, or am I moving? I mean, am I moving too fast? You can't keep up, or I'm going to keep going unless you tell me so. All right. Yeah.
About that. I mean, as I understand it, cows give off.
Yeah.
When you think about these other animals, really they're not giving off as much.
Sure.
So it's like,
yeah, a lot.
There to be such a big poultry amount and
really giant facilities. So we talk in terms of a made up thing called animal units in livestock facilities. So an animal unit is 1,000 pounds of animal. And so one dairy cow, like the big black and white ones, the Holsteins that you see, those maybe are around 1,400 pounds. So that's more than one animal unit. And you get permitted when you become 1,000 animal units. And so it takes a lot of pigs that are 250 pounds or 600, to make that same equivalent, but they certainly have them. So if something's permitted, it means they have that many animal units, but it might take a lot more. But yeah, you've got a lot of barns with a lot of animals going in. And you'll see, you don't see as many beef, because sometimes beef there are concentrated facilities, but if you let them out into like, hey, I'm using the shared grazing land, you're not gonna probably go out there and pick up, not to say that they don't do that in some countries on a smaller scale, but it's just not something we do here. Okay, so one of the things, so I downloaded this, you're gonna see, there's all these new under construction. So I wanted you to see like, back here, we started to see some growth. There were some changes in policy and some drivers try to get digesters installed. A lot of, in Wisconsin, they had some like, they had a little bit of policy shift. So here people could get like a rate kind of around 10 cents a kilowatt hour to produce electricity with their digesters. So we saw some growth there, and there were different grants available. For comparison, how much do you pay on your electric bill per kilowatt hour? Yeah, so they were getting paid about 10 cents. I would say the break-even point for a digester is maybe 8.5 cents or something on an agricultural facility, somewhere around there, maybe 10, maybe 7 if you're really great and efficient. So they were getting paid 10 cents, but how much does the utility buy coal power or other fossil power generally? Do you know that number? Maybe 3 cents, something like that, 3.5. So they were paying more. So there was incentives to have them pay more for this energy to fill a renewable portfolio. I don't know if people know a lot about renewable portfolios, but it was tried to incentivize. Some states have them where they say, hey, we want to get this percentage of our power from this. And so they create some incentives to be able to fill those renewable portfolios. That got filled, they use a lot of hydropower. So our renewable portfolio is still pretty low. I don't think it's changed since then. So not a lot of driving investment in that direction. all of a sudden we see this growth here. And I mean, there were other states along the way. Vermont was like popping little ones in all the time. They were giving a ton of money. And then all of a sudden we see this growth happening here. What's happened is we're not making electricity anymore, or at least a lot of digesters, they're shifting to make compressed natural gas or renewable natural gas. Some people call it different things. And so that shift has created, and they made another policy in a different direction, and it has really affected the growth, right? So I was just talking to my graduate students saying how boring I think talking about policy in classes and stuff, but it is the thing that changes things, right? So I as an engineer always want to I'd rather look at some data and build this thing, but policy really is the important part that's recognizes how we see change really push through. So if you're interested in policy, make that happen for us. So you can see this is just kind of another one. You'll see this was combined heat and power up here, the number of projects in the US. AgStar likes to track a lot of this data. So if you ever want to talk or look about digesters, EPA AgStar for agricultural ones, you can go there. They have these like an Excel database. You can run all kinds of numbers and look at the projects in an area. But you can see here this CNG, this is the compressed natural gas. Like the growth in those projects has been huge recently. You can see there's something else they're calling pipeline, which they're injecting, but you're really seeing a lot of that growth. I mean, some people will just burn it, right? You can just burn it for a boiler to heat stuff. You can produce electricity, and then the combined heat and power where you're taking advantage of both. I think, yeah, so a huge number of those RNG projects. The other thing I wanted to note, I was trying to remember what I put this slide in here for. So we have about 289 digesters in the US, which in about 2020. And so in that recent growth, right, that's another, we're almost doubling or 50% above where we were in a very short time, right? So it's all being driven by this conversion and collecting that gas and using it with that policy in a different direction. Does anybody know how many digesters they have in Germany? So they're much smaller than we are, right? They have like 10 or 13,000 or something, right? So comparably still, we are way lower than what the potential is in terms of how much livestock could handle, but we haven't seen the growth, right? Because they had a lot of policy incentives where they were able to install a lot of digesters at a time when they made a policy. They had a feed-in tariff system, and I think that was paying people maybe around 30 cents a kilowatt hour or something, right? So if you can make 30 cents a kilowatt hour, people will invest the money. It's only costing you maybe 10 to make it. That's a big, there's a lot of profitability there, and then you see an expansion. And how is Germany doing compared to us in terms of their renewable energy portfolio? Right, so it really is driven by some of that. Not that I want to just keep driving this home. The other thing is we have all these projects, but the big thing is right now, the CNG is going in on systems that are bigger. So they're really trying to target the large scale ones because that's where they can make the most amount of money, right? You've got a big scale project. The bigger the digester, the more farms you can put into one. That's where, when people started doing this, I was getting a lot of phone calls. Hey, which farmers want to do this? They all, a lot of the companies calling that were trying to invest in this kind of stuff were like, hey, who's the biggest? We want the biggest farms. We want the people with the most amount of animals. Because, if you're looking for money, the economies of scale, you really can make these projects more profitable at that. Not that there isn't a smaller scale that you can make money on, but everybody wanting to make money on is going to go for those higher price ones first. Good, I already made that point. So again, the system, we're just putting the feedstocks in a tank, right? There's not really a whole lot going on in there. There's some mixing, but the microorganisms are already in the influent. And so really you're just kind of mixing them around and then providing the environment for the microorganisms to thrive. So this is really what I always think about microbiology. When you're using it for composting, for digestion, for a treatment, for a processing system, whatever you're using it for, You only usually need to seed the microorganisms, right? And then they'll explode on their own if you can provide the conditions for them to thrive, right? I was reading something, someone who was studying gut microbiology, get out of my topic area, whatever, was saying some similar things, right? You can't just put one thing in this particular tank and think it's gonna thrive if you don't give it the right conditions, right? So the key things for digesters are temperature, right? The temperature of this digester is really critical. The warmer it is, the more methane the microorganisms produce. We run most digesters at mesophilic ranges, which is around 100 degrees Fahrenheit. And then you increase and you can get up into maybe 140, we call that thermophilic, up in that upper range. So at that temperature, you produce more gas for the same unit of feedstock. But what is like a, why maybe do you think not everybody does that? Well, sure. So you're wasting some energy. And so it's also harder to operate at those temperatures. You really could make the tank smaller. Some people run at like a mesophilic at about 100. You'll run a 28, 25, 21 day retention time, something in there. If you're running at a thermophilic temperature, you're talking maybe 5 days. So you can make the tank a lot smaller. The tough thing is the microorganisms that the methanogens that run at that higher temperature are a smaller subset, right? Down in the mesophilic, there's a lot of bigger range. Why do you think having more of this kind of microorganism might be an advantage to an operator than to have a smaller subset that might be more efficient? I mean, yeah, absolutely, right? So if I'm at this, what they found is you might have some advantages with this thermophilic system, but running it can be difficult because if you mess something up, you get something in the feedstock that they don't like, you might kill those more or make them inactive. And so they found most people feel like the resiliency at the mesophilic range is worth it in terms of operational efficiency and that kind of stuff. Yeah.
Question online. How would this vary from a distillation?
I don't know. Maybe somebody else knows. I don't know the specifics of a distillation system. Anybody?
Different out different components, separate out the different.
Sure. Sure. Yeah, and I guess I would say you don't want things probably to get as hot as you would in a distillation system because you'll kill the microorganisms. And you're not necessarily trying to separate. You're not trying to change the chemical properties to then capture something. It's a microbial process that they're producing a side product, but maybe I'm wrong there. They do release a little bit of heat, but it's not a huge amount. That's what. No. They use a lot of the either biogas to heat the system, or when they were running combined heat and power, they were using the heat and re-entering there. Mm-hmm. Yeah.
Are those being to take care of
Sure.
Stocks for their animals and running an AD out of it.
Yeah. I would say it's a mix, but still, I think a lot of the farms are running them. You have to be to a certain size. I think that operationally, that then it takes to then afford the labor. I would say it's like a shift back and forth. So the farms might not be located in a geographic area close enough for it to make sense for another operator. What I've seen is people try to operate systems remotely, or try to, like an engineering firm might want, or something similar might want to run these digesters, but the distance apart they become, They're using a lot of technology, so we do see some able to do some remote components, but the need for daily activities for somebody to be there is really necessary. And, you know, agricultural, I would say, you know, I'm generalizing, I'm gonna, usually not the greatest idea, but sometimes they like to operate their own things. They don't necessarily, you know, they might be, they sometimes think, and rightly so, am I losing potential income by giving this stream to somebody else over here, right? And so if you allow somebody to do that, then they're taking your manure and they want a lot of the rights and profits and other things that come. They also are taking on some of the risk, but it's on your land. So you're seeing a different, it's different everywhere. And so some will come out with contracts where they're negotiating and allowing the investment firm to own a piece of their land. But I would say a lot of producers aren't so into that, but that also depends upon where you're at. So I would say you see a lot of developers, maybe not always owning the systems though afterwards. So this was, I was also going to make that point of like, this is big and I don't need you to know everything, except this graphic is just kind of showing like the cow is like what the farm was built to do, right? So they have all these things and hey, I'm already doing all of that, right? I'm producing, I'm getting feed, I have all these animals, I've got veterinarians, I'm doing all this shit. And then there's all, you're adding on all these, right? So, you know, trying to put a digester in where you have a, I'm gonna like getting to the point of biogas upgrading and you're trying to decide which, you know, hydrogen sulfide removal system you want to decide on, right? That's a lot of choices to make. And you usually hire an engineering firm to help you put this together. But then if you're operating it, you have to know all these systems. So it's a lot more to handle. I think when I first started working here, a lot of people were having challenges and it was taking years for them to get the fluctuations of their system under control. And so I think they were finding like, whoa, we need way more labor spread out amongst people. And so then I actually saw a lot of the firms getting to like using some industrial efficiency techniques and trying to run some certain kinds of maintenance, you know, just taking on roles that I think a more an industry side would kind of bring to them. Not that they're not an industry, but on the engineering side, trying to bring in some of those lessons. But it's a lot. So I keep switching gears, but back to the digester, you can put all kinds of things in it. You can put in anything that's organic, can go in as feedstock. We don't see as much of this now. We would call this co-digesting. Oops. It's really great because you can see this is biogas yield, cubic meters of biogas per ton of the feedstock you put in. And you can see that manure is actually really low. The production of gas from manure isn't really that high. But you've got all this manure in one spot, right? And so you can feed it into the system. And so it's there every day. It's got what we call buffering capacity. So it's really great in that. Otherwise, you might need to add things to make the digester so it didn't get too acidic. But you'll see like fats, grasses, other things, they actually have a lot more capacity to give off more gas. And if you think about it, that's because the animal already used up a lot of that potential, right? And so then you're just using the manure. So there's a lot of reasons to do it. There's a lot of reasons to add other wastes. And when we were at a different thing, one thing I was talking about is policy has a tendency, it can do great things, but it also creates shifts in term that maybe aren't so great and kind of sidebar things you don't expect. So with the policy I'll talk about in a little bit, we had a shift from co-digestion to most farms don't co-digest anymore because of the way that they differentiated some of the things. The D3 you get more money for, with D5, if I co-digest it, I might land in that space. And so to get more money, you don't want to put other things into the manure. And so that policy has led to us not adding some of these waste products into a lot of the digesters, even though they might be able to make our systems more efficient and produce more renewable energy. We don't do it because it ends up, the policy kind of hurts that. Now there's people trying to correct that, and I still think the policy is trying to do something good, but that had an impact. In Germany, what happened was in some places, the price was so high that they were like growing stuff to put into the digester. And they were using diesel and all other non-renewable things to make this thing. So then it was like, wait, are these environmental outcomes really what we were trying to incentivize? So the policy, you do have to be really careful with how you place things, but they adjust, you know, you can always adjust things. It's good to try. Did you have a question? Sure. Yeah. So I would say like used fats, if you can get those from like, some people would collect them at like restaurant or something, like waste oils or other things. Used fats are like when they butcher animals, right? You can get some of the fat from there. So I think in bigger terms, you would go to like an industrial collection system, where, you know, one of the digesters out here they would drive up and it would be like a tanker full from a industrial process where they were doing some kind of food production. And then they would have this waste fat product.
Biogas yield, but actually methane. But I understand.
Sure.
But how does it vary with manure and say?
Yeah, sure. Yeah, we can. So the question is, how much methane, I'll start there. How much methane is in biogas? It's usually around 65%. It can be 60, it can be a little higher. A lot of times we'll do something like, and maybe this is one where it's methane. Actually, this is biogas yield, but you could do methane yield if you wanted to look at a different parameter, or methane yield per amount of carbon. So there's some other things we look at to try to look at the efficiency of the system. But the second part was, remind me. So it was, what is the percentage? Oh, in the feedstocks. So I would say the conditions are more what drive the percent of methane. So you can get a little bit more if you, with a little bit different feedstock and a little alteration. But some of the times what I've seen is like, oh, this one's a little bit warmer or has a longer retention time. So it takes longer, but my methane content kind of came up a little bit. But usually we do other, you know, method. In the end, people only care about our methane. So they're doing the math to understand, to represent that back and make decisions that way. But in this, I think a lot of these graphs were just made with assuming it was the same percent methane, which is generally around 65. Mm-hmm. Yeah. Sure. Sure. Mm-hmm. Yeah, absolutely.
I'm curious about how, like, what are the drivers for
Mm-hmm.
your intent?
So how would that affect their credits if you use different feedstocks?
Well, I just don't know what their carbon grass is a feedstock. Biogas. You know.
I don't know that off the top of my head. I'd have to get a chart, but
We had our capstone team last. Agricultural waste get a bigger benefit because they're capturing the methane that would otherwise be burning it or whatever. So you get a much bigger greenhouse gas benefit.
Oh, I see.
so the thing is you're avoiding losses from storage and land application. Some of these other wastes have that similar reduction where you'd see those losses reduced. Others don't, but to me, you kind of have to map out the whole system. And they have some on the LCF website. They've put some base numbers up there. I just don't know them off the top of my head. Good question though. All right, so there's a few different types of digesters. The main two that are out there are this is a completely mixed system. And so what happens here is manure or waste comes in, there's a few mixers within there, and then it goes out, right? It's just a big open tank. And then you'll see the top has that structure. There's actually a liner inside of there and then another layer, and then you use, typically you'll use some kind of air support to like be able to drive the pressure in there, right? So you can use that system, you can maintain the pressure when you don't have a ton of biogas, or you can even up the pressure to kind of drive the biogas out. So you can use that a little bit as a control system. In this system, we call it a plug flow system. A lot of these are now mixed plug flow, you'll see there, because they do have a mixers occasionally. But you can think of this as a tube. A lot of times it's in a U shape, but the idea is you put in one end and it comes out the other end. The difference I would say is that this one has a more defined retention time for each thing that you add, right? It has to make it all the way through the digester. Whereas in a completely mixed system, the way that you draw it, put in, puts in, and draw out, something could have a retention time. The calculated retention time doesn't take into account all the particles. Now, why is that important? Well, pathogen kill, degradation of the organic material, right? If you have a more defined retention time, theoretically that could be better, but they also show that the mixing has greater potential. I would say the data I see from this doesn't suggest one is so much better in terms of biogas production than the other. It's also hard to compare because there's nobody built two right next to each other that you can test on the same feedstocks. But I would say with the data I've seen, I don't know, you kind of get a mix of them. And not huge benefits from one to the other. Dry digestion. This is a system. This particular one is up in Oshkosh in this picture. In Germany, they have tons of these. There's only a few in North America. I think there used to be two, but I think another one or two might have gone in. But here, it's kind of like a bay, like a garage door or something, right? You open it. And this is not a mixed system. So you put all the feedstocks in, and then you close the doors, and then 4 weeks later, you open it up and pull them out, right? So it's sitting in there. It does have some systems where it's trying to control the amount of liquid that goes on there. So some will leach down and they'll recycle it and control the temperature. And then you'll usually keep a little bit of that feedstock and mix it in with the new incoming feedstock so that it can have the microorganisms mixed well enough to start your production again. So that's a dry. They use this more for like food waste, organic, municipal organics typically go there. The other kind of digester is like a covered lagoon where I would just have like a manure storage and I put a cover. I always want an updated picture, but we don't have a lot of these in Wisconsin because, right, we need to heat the systems in Wisconsin because it's fairly cold here. And that's really hard to do in this kind of system. So you see these more like those giant circles of the wine ones down in North Carolina. You see a lot of these. They're cheaper generally to implement. And then you just capture the gas up there, but they're a little less efficient because you don't have as much control. This is a picture of out here in Dane County. They built this in 2011. This is the community digester, so 3 farms give into one. I was just talking to the people that it's online now. There's a BC Organics project that's even more cows giving into one digester system, right? So there's some advantages to that. You can take those economies of scale. There's some difficulties in that, right? There's a lot of planning that has to come. A lot of farms have to agree to something. In a farm too, they take the waste back, right? And so I would say a lot of people are worried about pathogens and other things coming back to their farm. So there's some biosecurity issues that come in with this. Biosecurity isn't as big of an issue for dairy systems, really big for poultry and swine. It's still a concern, but just some notes that there's a lot of difficulties and people are like, oh, let's just put some more farms together. It's a hard thing to get everybody to agree whose site's going to go where, what are you going to take back, who's going to be financially responsible if there's like a pipe break between the transfer from here to there. In this case, they're piping underneath the ground, so they put those pipes in. Those pipes are pretty expensive. I want to say 100 and something thousand per quarter mile or something. So running underground lines gets very expensive very quickly. So these particular farms, I mean, it's the weirdest thing that I've seen. 3 huge farms, they're like, not very far. If you could throw a baseball decently far, you could hit all of them. That's not a really common thing. You know, a bigger farm usually isn't located right next door to another bigger farm. So sometimes getting these within the vicinity to have that kind of thing. What we are seeing more common though is, I think in California, they're seeing a lot of this. I think we're going to start to see a little bit more of it now. I saw one farm I heard of putting a system in where they can take and get biogas from other people. So when we're converting and pressurizing and treating, maybe we don't need to make those processing systems for the biogas everywhere. Maybe we could put the digester at the facility and then just truck or tank that. There's still costs related issues with that transport. There are some small scale digesters, they open and close. This one's still open. It's a little tiny one that they use for research. That it runs on a real farm, but UW Oshkosh. Brian Langolf helps operate this system. I've worked with a few other small scale ones. They go up, they operate, they don't, they do. It's just really hard to keep them financially viable at that scale. You can have micro scale digesters. This is one we built in Bolivia by the rainforest. There's lots of tiny, the technology is not, you know, you put shit in a tank, it's not that difficult. You can direct burn, so you can directly burn biogas. There's only some minor adjustments to be made, particularly from natural gas. We modify a lot of natural gas systems in Uganda where I work, where you can run that. You have to change some orifice things and whatever, but you can get the burning to be pretty easy. I will say electrical generation, combined heat and power. This used to be the thing that everybody was doing. There's some challenges here. Even though I said hydrogen sulfide was a really small part, it does a lot of damage to the actual system. So they have to buy the gensets are like, have to have this coating lining everything, and the oil changes, all the maintenance has to be much more frequent. I saw someone try to, I can never find this picture, I wish I had it. Someone tried to run biogas through just like a little generator that wasn't designed for it. And there was like this giant hole in it that the H2S ate in it. So it's really corrosive. And so you have to have specialized systems. That's why the electricity production is more expensive. So if you could remove the hydrogen sulfide really cheaply, then use something on the back end, that's a great idea. Removing hydrogen sulfide hasn't been a cheap thing. You know, we're working on things to do that, but it's still taking a while. These are some old school absorption chillers that we use in Uganda. We modified these so they can run right off the biogas. And so that's kind of cool because heat in some places is not really what people need, but then chilling capacity was really helpful in those areas. So let me check the time here really quick. All right, we're doing oh shoot, okay.
You want to go through the.
All right, let's make sure, I'm just got a few slides and then we'll go to just talking questions. I just wanted to get to, this is the thing we were talking about that was driving all the installations, right? Where we're going to pipeline injection and the compressed vehicle fuel. Well, there are a few fuel facilities that actually scrub and compress right on site. That's not typically what's happening. You're injecting into the grid, and then though somebody theoretically is taking that out, you're assigning RINs or credits to those things that you're injecting. Somebody else is using that for compressed fuel somewhere else. There's a lot of tech. You can use water scrubbing, absorption system, membranes, all kinds of things. They're generally pretty expensive, millions of dollars of capital costs in these systems, and the operating costs can be quite a bit as well. There's usually trade-offs, right? I pay a little more in the capital, maybe a little less in operating costs. So it depends upon what you're looking for. Again, this is a processing system, not treatment. So in terms of the digestate, it still has to be land applied and handled. There's a lot of odor reduction, pathogen reduction. Pathogen reduction, I know this is a terrible giant table, but it's somewhere above 90%, right? So you're seeing a lot of pathogen reduction through the digester. What is important when we did some risk assessments and other things and how you use a manure, if I live next to a farm like this and I'm using groundwater, I'm gonna really love if you're putting digested. I'd rather the manure be digested. Your risk is highly reduced. But as a microbiologist I used to work with, I always said, if you have so much in the influent, a 90% reduction doesn't mean that doesn't have any risk, right? So while it's better a lot of times than using just straight up manure, it's going to improve that, it's going to increase pathogen kill. It doesn't mean it's perfect and you should put it anywhere.
Are there certain pathogens?
We didn't see that. We saw some that didn't die off that are more hardy. They do show that there are, you know, with changes in pathogens that there could be some resistant strains. We were only, you know, we measured a whole suite of them. So we didn't see anything that we saw as resistant, but there could be many that we weren't measuring out there, right? So we were running some ones that are zoonotic, that are common transmission from humans to animals, and then a few specific to animals. I hate doing odor research, but there are a lot of other people have, and they show odors reduce. I think producers talk about, there's one producer who used to tell me they used to send all of their neighbors to the dells when they applied manure over the weekend, because they were just like, it was cheaper than dealing with the complaints. But then they got a digester and they were like, nobody even knows when we're spreading anymore. So that kind of shows the difference. A lot of other people say something like, you know, I used to take a rainstorm for the odor to go away. And as an environmentalist, I'm like, okay, what do you think that's happening there, right? That's not good. But they were like, no, now, you know, it just infiltrates and it don't smell at all. It does reduce if you have antibiotic degradation. There is some antibiotic degradation. Some of the pieces still remain. Antibiotics could reform. Composting is they've shown to be a better source of that, but you do see some of that. All right. The last few things I want to say is there is a big global warming reduction. When we were talking about before, why are we seeing credits given to this? Well, you're capturing that methane. Methane, if you're talking about a 100-year horizon, you know, maybe you're giving it a CO2 equivalent of 28 or 30, right? So if I capture that one methane, convert it to a CO2, I've just, you know, reduced that by 30 times, right? So that's the math generally that is really changing it. Now, we use more technical ways to show what's lost in storage, what's lost when you land apply, and then when you shift to this new system, there's still methane there, right? We've been actually using some new systems where we used data from some existing farms to try to look at what that the degradation of solids is and the organic degradation, so we could better refrain it. And it's still, the reduction is really great. But there are some negative things, right? It increases ammonia emissions. So this is a big thing that's happening on those swine farms that I showed you. They have some big issues down there where they're getting really concerned. I had a reporter call me from California. We're putting in all these digesters. Are we creating a huge issue with ammonia? I would say what I try to tell people is it's still a good thing. Environmentally, I would say, you know, it's good to introduce these systems, produce renewable energy, reduce the methane losses. We have additional ways that we can mitigate the ammonia losses, right? So once I produce the manure, I can inject it, I can do all these other things to reduce ammonia. So I would rather we do the digester, we use some additional things to mitigate that unintended consequence. The reason this happens is through the digester, organic nitrogen mineralizes into ammonia, and so you get more losses if you were to treat it exactly the same in storage and afterwards. So it's an issue, but I think it's manageable with other practices. Okay, since we're running out of time, I'm going to skip some of these. The one thing I want to say is, so economics is a really big driver. This was something that someone put together, I think it was Brian Winkle, and was showing at the operation of a digester when they were running it to produce electricity. And they had, I think, an 8 or 10 cent per kilowatt. I think it was 10 cent a kilowatt hour. And their annual operating and maintenance was about 1.2 million. And they made about 1.2 million with that electricity cost. He was saying they thought they could get it better and kind of bring it down and make a little bit of money. And I saw other people paying back their systems in a reasonable amount of time for farms. Not the 2 years that a lot of industry returns want, but for farms have a longer term kind of mindset for that. So they were doing all right. What you can see now is the drive of the installations are from the Renewable Fuel Standards and the Low Carbon Fuel Standard. I don't know if you talked about those in class too much, but you get a RIN number. In the cellulosic category, which digesters fall in, if you just manure, you can get the D3. And so that's about $3 right now. And if you turn that into BTUs, that's maybe around $40. These were the most recent prices I find out there. If you end up in the D5, that's about $2, but these fluctuate, right? So
for a while, D5 was maybe at $1.50. So they're getting closer, so maybe the difference doesn't matter that much. And the low carbon fuel standard is currently at about 86. When it started out, it was somewhere closer to about 200, but that's per credit. So you kind of have to convert that. And with my estimations, that's maybe around 20 MMBTU. So you're getting a lot more right now from the renewable fuel standard than the low carbon fuel standard. It used to be reversed, right? And people were getting more from this other one, if I'm getting all of my numbers correct. But I will tell you, there's a lot of flexibility in this, right? In that low carbon fuel standard, you have to have a process and you get these values. And so depending upon what you input and what your practices are, that number could fluctuate. But what I wanted you to understand is that these are really driving that investment, that this is a much better payback. And for the time foreseeable will be there, that people think is reliable enough for them to drive this new investment. There's a lot of tools out there. We have a lot of fact sheets. This virtual farm has, if you want to look at a digester system there, you can kind of go around and take a look at some of those details. And then if we have any time, I'm happy to answer questions in the last few minutes. All right, I made it through those. Any questions?
Is that fuel?
There are two different ones. So generally, the low carbon fuel standard started out of California, and CARB made this kind of rule that they were going to offset a certain amount of things. I think they started out with like 10% or something. And so they were making people who were consuming certain types of fossil fuels were going to pay the money to offset this. The renewable fuel standard is others who needed to meet the threshold of like, I'm producing fuels and now the EPA is saying I have to offset so much of that production with these by paying these for these other renewable identification number fuels. So that money is coming from people using those other types of fuels, producing those other types of fuels that are then required to pay and offset some of that for these other ones. If I know it's very generalized. You can
Say from the, like the
Yeah.
source of it is the energy. So there was a first RFS that started. The energy bill.
that top one. And then the other one was developed out of the state of California, and Oregon has jumped into that. And then I think Washington is moving towards it or is in it. I don't know, more in that realm. Other questions?
We have an online question. Roger's asking, and you kind of addressed this of the incentives of fuels versus electricity, but could a series of, his question is, could a series of digesters be used for heat shaving?
Absolutely. Yeah, that's why I said, I think they were kind of showing in some grids, like microgrids or other grids where, or even, the large grid that had a lot of potential for storage and use at nighttime, peak demand, using it in the system is where a lot of the potential is, even if it's, because you're not going to get, even with digesters, even if we filled up all the potential, it's still not going to be a huge percentage of our energy production, right? We just, it's unlikely that we'll see that, but it can play a role in the entire system. All right. Well, there's an engineer talking too much about policy. Hopefully you learned something and you can fill in all the other policy holes with others that I'm sure you'll see here. All right. Thanks for coming out today.
Thank you so much for the
Yeah.
presentation.